In this unit, we'll look at authentication. The main areas we'll be covering is that we need to identify what it is we're really authenticating, some of the weaknesses and issues related to usernames and passwords, the issues and methods of biometrics, the usage of the hash signature to identify things and to authenticate, and the usage of digital certificates to authenticate entities. At the end, we'll look at a modern infrastructure which might be the way forward for the future, which is card space. Okay, the three fundamental principles of security are authentication, confidentiality, and endurance. Authentication involves authenticating users, devices, servers, connections, and so on. In fact, every single element of the communications and data storage should be authenticated in a highly secure system. The second principle is confidentiality, and this keeps the data secure. Typically, encryption is involved with confidentiality. And then finally, we need assurance in that there is some integrity in the data and of the systems. It is these three foundation principles that gives us our viewpoint on security. Okay, so some of the key issues that we have are: how do we know that it was Bob who really did send the data? Because anyone can get Alice's private key and then use that private key to encrypt some data and then say that they are Bob. So in this case, Bob sends using Alice's public key and everything is fine, but unfortunately Eve might be there and send to Alice and pretend to be Bob. Along with this, how does Alice actually know that the data hasn't been tampered with? We can see here that Bob has sent a message. Eve unfortunately has tampered with it, and it might be difficult for Alice to determine that the data had been tampered with. Along with this, the next issue that we have is that how is it we can actually send a public key to the other side? So if Bob wants to send to Alice, how does Alice send the public key to Bob? And then also, can we really trust Bob to authenticate himself? So in this unit, we'll see the usage of Trent, who is some trusted person and is trusted by both Bob and Alice to properly authenticate entities. Okay, so what are some of the methods that we might use to authenticate? And what is it we're trying to authenticate? Well, obviously, in the past we've authenticated devices, fairly simple methods such as determining their network address or their ID. We need to identify systems, email servers, web servers, DNS servers, and so on. And we also need to identify users, because users tend to be the main entity, the main end entity that we're actually trying to identify. In the past, we've identified devices which are maybe owned by a certain user, but that really is no substitute for identifying the user themselves. And we also need to identify data, whether it be a database or a message. Okay, so where is the authentication happening? Well, the authentication can be end-to-end authentication. In this case, the user authenticates himself to the final thing, which in this case is the service. There might not be authentication in between, but the end user is authenticating themselves with the end process. We might also have intermediate authentication, where part of the chain is authenticated. In this case, the device is authenticated to a server. We can see the weakness of this is that the device could be used by another user. Also on the server, the actual service might not be actually authenticating the device or the user. So if possible, we need complete end-to-end encryption, authentication. Along with this, it would be useful to have intermediate authentication along the chain. So the two ways of providing the authentication is typically one-way authentication, where the server sends its ID, typically a digital certificate, to the user. The user checks the ID and makes sure that it's actually valid and then makes a connection. The weakness of this is that the user is not authenticating themselves to the server. We can also get one-way client authentication, where the client, before they connect to a server, must pass their identification to the server. And then we can have, in the best case, mutual authentication, where IDs are passed on either way and the IDs are checked on either side. With one-way authentication, we typically see this on the internet when we use a secure connection using SSL, such as with HTTPS, FTPS. When a connection is made, the server sends its certificate to the client for them to check. With one-way authentication, we might have a device which has a digital certificate. Then before we can log into the wireless access point, the certificate is sent to authenticate the device or the user. And mutual authentication is in systems such as PEEP and wireless systems, where there is an identity check on either side. Okay, some of the things we might use to identify users include usernames and passwords, which have been used traditionally, but as we'll see, are becoming fairly weak in terms of authentication. There's digital certificates, which are a fairly good method of authentication, but as we'll see, suffer from several issues. Increasingly, there is the usage of token cards, which might have smart chips in them or RFID cards. Soft tokens, which are installed onto the machine and are software cards. Session keys, passphrases, and biometrics. Devices might be authenticated with their actual name or ID, a digital certificate that they might have, a passphrase, the network address, or even an encryption key. Increasingly, authentication involves not just one thing that is authenticated. And the basic principles that are laid down for authentication are something that you have, and that could be a digital certificate, could be a network address, or it could be a smart card. Something you know, so it could be your username and password, your mother's maiden name, and so on. And then something you are might be your palm prints, your retina scan, fingerprints, and so on. If possible, in a highly authenticated system, the three things should tie up, because it is typical that someone can determine one element of it, but it is very difficult to determine all three areas. Each of these areas vary in their ease of use and also in their robustness. Usernames and passwords are usually fairly easy to use, but they suffer in terms of authentication. So we typically use things like aging usernames and passwords, and they become more robust. Digital certificates are reasonably easy to use and have a reasonable level of authentication. As we go up, the uses of soft cards and tokens are not so easy to use, but are highly robust, and at the very top we have biometrics, which are sometimes difficult to use. Okay, so let's look at usernames and passwords and look at some of the issues involved with them. the main problem that we have is that passwords are typically easy to guess, and they are often weak. Along with this, passwords are open to social engineering attacks, where someone can actually ask a user what their password is, and unfortunately many users will actually tell them back again. And along with this, we are being forced to create longer passwords and change them on a regular basis. Unfortunately, this makes the passwords difficult to remember, and users often go back to the same passwords again and again, or just slight variations such as adding 1 or 2 on the end. So we can see here that there are, for a 10-character password, there are many possible permutations of the password. But unfortunately, most passwords fall within a standard dictionary, and it's been shown that the average number of bits per character in a password is only 1.3 bits per character. So the actual strength or size of a password is typically only 13 bits. So most passwords, as we can see, could be cracked by looking within a 2 to the power of 13 different phrases. So they are open to dictionary attacks. We can see here in 2006, Brown conducted a survey of the top 10 passwords and found that a good percentage of them were fairly easy to guess. We can see here QWERTY as a standard, 123456, Liverpool password 123, and so on. The length of the password is obviously important, as the longer the password, the more difficult it is likely to be able to guess it through a dictionary attack. You can see here that Snyder did a survey in 2006 and found that password size was between 6 and 9 digits, which is seen to be fairly weak from the point of view of a dictionary attack, and stronger passwords were virtually unknown. We can see here that passwords can often be guessed, in that many users use the name of the dog or a favourite colour, the mother's maiden name, and so on. Okay, so let's look at if passwords and usernames of passwords are not becoming a favoured way for users to authenticate themselves. Let's look at biometrics. And biometrics involves using a physical attribute of a user to authenticate them. There are, though, various issues in the usage of biometrics, and we'll look at these before we look at the actual techniques. One of the most important areas is acceptability, in that users will not adopt a biometric technique unless they find it acceptable. So techniques such as DNA and face scanning are at the edges of being not acceptable from a user point of view, as there are many issues in it. The usage of fingerprints inside a medical environment may also not be acceptable because of the spread of disease, whereas handprints or fingerprints in general might be an acceptable method of biometrics. Along with this, there's the distinctiveness of the biometric technique, and this is looking at the attribute which makes the characteristic unique. Fingerprints are a well-known method for determining this, and that tends to be fairly distinctive for each user. The colour of someone's eyes is obviously not a completely distinctive method, but it may be that the shape and the layout of the eye is a distinctive one. Permanence is obviously an issue, and that typically relates to how the attribute changes over time, such as for skin flexibility or hair length and so on. There is obviously an issue related to collectability, in that some methods are non-obstructive, where the user doesn't actually have to be within range of the scanner, but others actually do. And then there is generally performance. How good is it at identifying users? If we get too many false authentications, then it may cause the whole system into disrepute. So fingerprints have fairly good performance, but for law enforcement there are standard techniques which need to be used, and these include DNA, fingerprints and written signatures. For things like host and network access, an iris scan, face recognition and handprints can be seen to be useful methods. And there's also the universality, and that's how much the human features translate into characteristics, such as in fingerprints, the iris layout, vein structures, DNA and so on. So in this part we'll look at biometric methods. Two of the most credible methods that we can use in biometrics are DNA analysis and fingerprints. With DNA analysis we get a highly credible result, but unfortunately there are moral and legal issues. It is also costly and can be fairly slow in analysing. It is also evasive, but new methods include hair and skin samples which tend to be less evasive. Fingerprints is now one of the most widely used methods of authentication and are typically seen in notebook logon systems. Unfortunately, the quality of it can be variable, especially if there is dirt on the scanner or if there is dry or cracked skin. Iris scanning is an excellent method, and it involves looking for the corona, filaments, cyst pits, freckles and so on. New methods have even been applied to mobile phones, which can take a photograph of the iris and try and identify the user. It is typically difficult to trick the system, but is affected by the wearing of glasses. It is also fairly costly to implement, and its accuracy depends on the resolution of the scanner. Retina scans are one of the most credible methods, and it involves shining a light on the eye and looking at the blood vessels at the back of the eye. Unfortunately, needs careful alignment for a credible scan, and some researchers have identified that it might cause long-term damage to the eye. Face recognition is a technique which is often used in remote scanning of users, and it typically involves taking a 2 or 3D image of the face and trying to align it with a known face. This image is then analysed for distance across the nose, between the eyes, the size of the eyes, size of the mouth, length of the nose, and so on. Unfortunately, it can have poor matching if the scanner is fairly far away from the face is fairly far away from the scanner. Hand geometry is one of the most widely used methods now, and it typically involves scanning a hand for key features such as the lines, the length of the fingers, and so on. One of the great advantages is that it can be contactless, where the user doesn't actually have to touch a screen, and is now used in access to buildings and room access. Vein pattern recognition is one that is taking off in a great deal, and it typically involves shining a light on a finger in a scanner and then analysing the vein pattern inside the scanner. Another technique which is used, but the results tend to be fairly variable, is voice recognition, and that's analysing someone's voice in terms of a known pattern. It can be used remotely, especially in identifying users over telephone applications, and it typically analyses a limited range of words or passphrases. Unfortunately, it degrades badly with background noise, along with the changes of the user's voice, such as when they have a cold. Keystroke analysis is another area that has some issues, and it typically involves analysing the characteristics of a user as they type. It could be related to their keystrokes per minute, or it could relate to words that they always misspell. It's one of the least liked authentication methods, as it can be seen as a keystroke logger. Other techniques which might be used include ear shape, personal signatures, and body odor. A key element of authentication is the message hash. So how do we get a fingerprint for data? Well, this was solved by Professor Ron Rivest, one of the founders and inventors of the RSA algorithm, and he came up with an algorithm which allowed us to take anything, and user entity, files, data, messages, so on, and to create a standard fingerprint for them. One of the first techniques he came up with was the MD5 algorithm, and with this he created a 128-bit signature. And then when a message is put into the MD5 algorithm, we see here that we get the same size of signature no matter how much data has been entered. And we can typically convert it into base 64 or hexadecimal. The number of characters that we get in this case will be 32, because each hex character is 4 bits, so our signature itself is 128 bits. For the base 64, we take 128 and then divide it by 6, because we take 6 bits at a time. So we can see here, just by changing one character, we get a completely different hash signature. It has been shown that the MD5 signature can produce collisions on a fairly regular basis, where the same signature can be defined for a different word. So obviously, the more bits that we have, the less chance there is of a collision. So the SHA-1 algorithm was created, and this is a 160-bit signature. And we can see here it has a longer signature, and the chance of a collision happening are much reduced. So the key thing is that we can take a great deal of data. We could take one character, or we could take the whole of the internet and create a hash signature of it at any given time. So in this case we have a message which has one character difference. I can see here that the actual hash signature is considerably different. So if someone was to modify any part of a message or data, then it will create a completely different hash signature. One of the applications of this is that we could find the hash signature for certain files, for the whole file system, say for our system files, or we could do it to get the base64 signature. And then when the file system checks these files, it checks the hash signature. If it differs from the one which is stored, then that file has been modified and possibly cannot be trusted. So we can see here that digital certificates, as we'll see, also have a thumbprint. Here we can see the hash signature of this in an SHA-1 format. If someone has modified this certificate and it gets a different thumbprint, then it looks as if this certificate has been changed. In this part, we'll look at how a user or entity is authenticated using the private key. In the first part of this authentication, what happens is that Bob takes the message and then takes a hash signature of the message and then encrypts that using the RSA method, typically, with their private key. This is then added to the message. If Bob is sending to Alice, the next thing that must happen is that Alice's public key is used to encrypt the whole of the message plus the MD5 encrypted hash signature. So then after this we have our encrypted content which can be sent to Alice. Alice will then use her private key to decrypt the content, so we end up with the message and the encrypted MD5 hash. Alice then gains Bob's public key and then is able to decrypt the encrypted MD5 message and gain a result. She then takes the message that she's received and then puts it through the MD5 algorithm and then checks the two. If the two tie up, then she has authenticated Bob, as long as Bob's public key is correct. An extension to MD5 is HMAC. With HMAC, the algorithm uses MD5 or SHA-1, but applies a secret key to it. The secret key is then sent and the HMAC signature is then decrypted by this secret key. So if we look at an example, okay, so we have MD5 and SHA-1. We take a message such as hello and generate some hash signatures, and we should see that hello should give us the same hash signature each time. For HMAC, we have a message, which is hello, and now we apply a key to it, and then that creates the HMAC's signature. So in this case, a message of testing 1, 2, 3 with a key of hello should generate the right key. Okay, in this part we'll look at digital certificates. So the major problem that we have now is that how do we get the public key from one user to another? If Alice wants to send Bob a message, how does he get the public key to Alice? One way to do this is the digital certificate, and the digital certificate is a useful method for holding either a public key or both a public key and a private key. The key elements of a certificate are its basic details, who it was issued to, who it was issued by, and the date it was valid. The public key that we can see here, this is a 2048-bit public key. The issuer is key for defining the validity of the certificate and whether it's trusted or not, and the thumbprint. The two main forms of certificate are ones which just have the public key on them, and this is a certificate which can be sent to another user because it does not reveal the private key. The other type is one which has both the public and the private key. It is this certificate which should not be distributed. When a user gets a certificate, it's typically one with public and private key. If they want to distribute it, the private key is taken off the certificate and sent only with the public key. One of the main formats which is used is the PB7 format. In this case we have a text, base64 text file, which can then be imported into the system. We can see here we have Internet Properties, Certificates, then we have the certificate import. The PB7 file is selected and is then imported into the user's store and creates the certificate on the system. Other formats include PFX format, which is a binary format which can have a password in it. So now what happens is that when Bob wants to send Alice an encrypted text, then her certificate is sent. Bob takes the public key from it and then encrypts it. On the other end, Alice then decrypts it with her private key. For authentication, Bob will encrypt a hash of a message with his private key and then encrypt with Alice's public key and send the two things together. Alice then decrypts with a private key, decrypts the hash using Bob's digital certificate, the public key from his digital certificates, and can authenticate. So we have now authenticated and also kept secure. Okay, so a key element of this is that who do we actually trust? We can't obviously trust Bob to send his identity. So we now introduce a new character, which is Trent. And Trent is someone who is trusted to identify an entity. So in this case, Bob might send a digital certificate to Alice identifying himself, saying that he is Bob. but we can't trust that because Eve could have done the same. So we now need Trent to define credibility. On the internet, we have what's called the public key infrastructure, or PKI. With this, we can have trusted roots, and it's these trusted roots who are able to grant these certificates. So these might include VeriSign, Entrust, Microsoft Trust, and so on. So when Bob wants a certificate, he goes to these trusted roots. The trusted root should check the user and their identification and the usage of the certificate, and send the certificate which has been signed by the trusted root. The trusted root certificates are installed typically on operating systems as a default. So when Bob sends his certificate, it is then checked that it was the trusted root who signed the certificate, and if Bob and Alice trust the trusted root, then the certificate can be trusted. Unfortunately, this method suffers from the fact that the trusted root doesn't always correctly check the user. In this case, Eve has asked for the certificate and has not checked it, then is sent to Alice, and Alice will obviously think it was Bob. The main levels of trust that we have are trusted roots, and these are organisations which can be trusted to sign certificates, and these are signed for certain purposes such as secure email, server authentication, code signing, timestamping, and so on. Then Trent trusts certain organisations to be intermediate CAs which have trust in signing some things. And then the least credible of all is the self-signed certificate. In this case, we cannot really trust Bob to self-sign his own certificate. So let's look at a few examples. Are these real certificates or are they not? So the first one we have is signinebay.com. Is this real or is this not? We can see that it's quite difficult to actually tell if a certificate is valid or not. In this case, we have signed into eBay, and if the certificate is not in our store, then we will be faced with this certificate. In this case, there is a certification path back up to the root certificate, so the certificate can be trusted. In this one, the user gets Amazon e-commerce and it's valid until 2013. Is it real or is it fake? In this case, it is a fake certificate, as there are no actual root CA. The user is then given a security warning saying that you're about to install the certificate. Unfortunately, very few users understand this message, and a fake certificate could easily be installed into the system and incorrectly used. This one here, we have a certificate and it's global sign. Another problem is that the organisations for the CA are not understood for their names by most users. So global sign, domain, validation CA, real or fake? It is real. There is a full certification path, and global sign is one of the major organisations which create certificates. This part of the presentation looks at a possible infrastructure for the future which integrates security with authentication. And one of the best modern examples of this is Microsoft CardSpace, which is part of the .NET 3 framework. With this, we can create two types of card, a personal card, and the personal card basically just contains a few of the details for the user. The other type of card is a managed card, and with managed card This will be used for correctly verifying the user and can be used for online purchases, managed logins, and so on. The advantage of these types of card is that all the details which relate to credit cards, passwords, and so on are not actually kept on the user's machine, so that the user can easily roam and use their card on different machines. So when we create a card, we either have a personal card or a managed card. So this is an example of a personal card where the details are actually stored, and then when someone logs in, that card can be passed to the server. The server can then take off the details of the card. So some of the things involved with the personal card might include the card name, their picture, the date they created, the date of birth, and so on. Managed cards, though, are encrypted, and all the details which relate to the user are kept on a remote site. There is also a history on the card. So a personal card is typically used when the user logs into what's called the relying party. The relying party would be eBay or Amazon or so on. These are the servers which provide the main service. So you can see here the card is passed and then there is a login. But for purchases and with managed cards, then when the user wants to access the relying party, they contact the relying party and ask for a resource. The relying party sends back to the user as to what identity providers are trusted and how it wants the identity to be provided for it. The user then goes to what's called an identity provider. So these might be an identity through Google or Amazon or from a university login system and so on. So as long as the relying party trusts the identity provider to provide the identity of the user, the identity provider checks the user and the details, then gives the user a token. The token will have a certain time limit and so on, and all the details that are required for the user to be able to take to the relying party. This token is then passed to the RP, which will then allow the transaction to happen or not. The great advantage with this is there are no actual communications between the IP and the RP. And if the IP is trusted by the RP, then the communication can take place. So the infrastructure for card space involves the identity selector. It's up to the user to identify how they identify themselves. Might be usernames and passwords or a card. There is then the identity provider, and we might have a standard PKI infrastructure where we use digital certificates, or it might use, as we'll see in a later unit, Kerberos, and Kerberos allows for the issuing of tickets. A ticket can then be passed and then passed to the relying party, which can then authenticate it. So this is more likely to be the infrastructure for the future for online purchases and so on. It uses a new XML security language, SAML, and is completely built around XML standards. So as an example, as an analogy, we see this type of authentication happening where we go to the airport, we take our passport to check in. The check-in then provides us with a token. In this case, the token is the ticket, the airline ticket. We then take that ticket to airline security. We don't have to show our original identification passport anymore, and we just have to show them the token, and we should be allowed to board the flight. The key thing in this is the element of trust. The ID has been checked correctly here, and then a token is initiated and given to the relying party. With this we can now have a federation of trust, where we might have several places that there are check-ins, and as long as the relying party trusts these ID providers, then it doesn't matter which one of these is actually used. So can you see here an example of creating a card? Add a card, add some of the details. Then we can go to the Windows Live login in this case, and we can actually log in with our managed card. So there are no usernames and passwords involved. We can pass our card, the card is taken, the site asks for which card is required. Then we have a login, and we can see here that we have managed to successfully log in, and it will take the details. On our card itself, it will show all the details, the whole history of the transactions. As one last area, we look at email encryption, and again we come back to the PGP algorithm to show us an excellent example of encryption and authentication. With PGP, we have authentication and encryption, and the idea algorithm in this case is a private key algorithm. Private key has much better performance than RSA public key methods. So here we see the information to send. There is a hash taken off it. Then Bob's private key is used to encrypt that hash, so we get a signature plus the original email. This is then zipped up to compress it. It is then a session email key is created. Any key, random key, is created and is then used to encrypt the zip. Along with this, the key itself is then encrypted using Alice's public key, and then this encrypted key is added to the mail and then actually sent. On the other side, Alice will use her private key to decrypt the key and get the session key from it. She will then be able to unencrypt the email, unzip, get this back, take the signature, use Bob's public key to decrypt the hash, and then identify both Bob and the message. So the main conclusions is that we've looked at what we're authenticating, we looked at the problems with usernames and passwords, and then we went on to look at the biometric issues and methods, of which there are many, and then on to the hash, the main hash signature methods, and how we can actually authenticate using this hash key. Then we looked at digital certificates to see how they worked and some of the issues that we had with them, and then on to possible infrastructures for the future using card space.